It is time for 5.3, inverse functions and relations. So we're going to talk about inverses. We talked about relations way back in chapter 2. A function is a type of relation. So relation is the larger category. We'll also be touching on functions and remembering how to tell them apart. But what we need to cover today, first of all, I'm going to briefly say what an inverse is. We're going to get a definition there. Then we're going to learn to find inverses. We're going to do it from a list of ordered pairs because we can define a relation as just ordered pairs. I'm going to talk about how an inverse is related to the graph of its relation. So the relation itself and the inverse of that relation, how the graphs are related. You should be able to sketch or draw a graph of the inverse from the original, although that won't be on your homework specifically. You should be able to find the inverse if you have a function defined with an equation. You should be able to find that inverse too. So A and C are on your homework, but I am going to talk about B as well. Number 3, determine if the inverse is a function. We can do that actually before or after actually finding the inverse. We can determine whether the inverse is a function. It's the inverse either way. Sometimes it's an inverse function, and sometimes it's an inverse relation that's not a function. And lastly, we're going to learn how to verify that two functions are inverses, which is the last thing I will show you. So what is an inverse? An inverse is a relation that undoes another relation. That is, if, for example, if you walk to the left and then you walk to the right, you wind up back where you started. And that's what that's kind of the meaning behind inverse. In math, it's an operation that undoes some other operation, like adding to and subtracting to. They undo each other. That's what an inverse is. So the most important part about finding an inverse is to recognize that because they're supposed to undo each other, like if I have a function, like say f, and f of 2 equals 5 for whatever reason, its inverse is the function that, or relation anyway, that takes that 5 and turns it back into a 2. Or more generally, if f of x equals y, then f inverse of y equals x. So an inverse is going to be related to the original relation, but the x and the y are going to kind of be switched. All the x's become y's and all the y's become x's. And that's the most important thing to remember. Everything else about inverses is built around this idea. You got to switch the x and the y's. So if it's a table, the x column and the y columns are just going to switch. And my first example here, finding an inverse from a list of ordered pairs. This is R, is a relation. It's not a function, and I can tell it's not a function because if I stick in 1, I get 3, or I can get 0, because 1 could be either 3 or 0. And if I stick in 6, I sometimes get 3, and I can also get 0. So this is not a function, but it is a relation, and I can find its inverse relation just by remembering that the inverse undoes, or I'm going to switch all the x's and y's. So my regular function, which I call R, or relation, not a function, my regular relation will take a 1 and turn it into a 3. So my inverse relation needs to take that 3 and turn it back into a 1. Just switch the x and the y. For the point 6, 3, my inverse needs to take 3 and turn it into 6. So sometimes it turns 3 into 1, and sometimes it turns 3 into 6. Also not a function. So let's see, 6, 0 makes the point 0, 6. Again, just switch the x and the y. And 1, 0 makes the point 0, 1. Yet again, switch the x and the y. That's all we do, switch the x and the y. Every single thing here, switch the x and the y. So this is R inverse. It is the inverse relation for R. And these are just points, so all I got to do is flip them around. If it's in a table, you just flip them around. Now this particular relation is meant to be the vertices of a rectangle, I think. So if I graph it, 1, 3, 2, 3, 4, 5, 6, 3, 6, 0, and 1, 0. It's this rectangle right here. The relation itself is the vertices of this rectangle. If I graph the inverse, for which I should grab a different color pen. Hold on. Okay, I grabbed my red pen, and now I'm going to graph the other one, 3, 1, 3, 6, it's going to overlap. 0, 6, and 0, 1. So my original rectangle was defined by the first 4 vertices here. And it's this way. Now the inverse is defined by these vertices. But if you think about it, all I did was take all the points on my original graph and switch the x and the y. So you wouldn't really need to know or be listed the points. You could find the inverse as long as you can find points on the original graph. You can graph the inverse just by taking each point, 6, 3, switching the x and the y, 3, 6. So you should be able to do the inverse. Now, if you want to know if you did it right while you're looking at it, the thing about inverses and their original graphs is that they always work out to be a reflection over the line y equals x. So if you draw the line y equals x here, you should see, if you drew it correctly, your inverse is reflected across this line from your original function. And that's the graphical portion. As promised, for 2c, we're going to take a look at a function defined by an equation. F of x equals -1/2 x plus 1. And I'm going to find its inverse. So your book lists this in this section as like 4 steps, which is probably fair. They recommend you rewrite f of x as y because they think you'll get confused by f of x, which is reasonable. It's technically optional, but it's not a bad idea. And then you do the actual inverting step, which is the same as the previous inverting step, which is you switch the x and the y. So now x equals -1/2 y plus 1. If you're working with an example that has more than one x over here, all of the x's have to become y's, and all of the y's become x's. We, in Algebra 2, don't do stuff with more than one y. I don't think so. I'm pretty sure not. But there might be more than one x, although that makes it difficult to solve for the new function. So you don't see a lot of those. Once we switch the x and the y, in order to actually write this properly, we now need to solve for y. Right? To find the inverse function, we got to get this y all by itself. So after you switch the x and the y, you know what? Let me write this out. So you write with y instead. Then you switch the x and the y. And then you got to solve for the new y. The new y, not the old y. So I'm going to subtract 1 and then multiply by -2. And then I can rewrite this back into function notation. Although it's not f anymore because I switched it, it should be f inverse of x equals -2x plus 2. So you write it with y, you switch the x and the y, you solve for the new y, and then if its inverse is a function, you should write it using function notation. Go back to f inverse, but you should write it as f inverse. Now, theoretically, you never needed to use y. You could skip this step and write f inverse over here, and then solve for f inverse. That's also fine. But if you're uncomfortable with that, you certainly don't need to do that. Most students, especially the ones who, get scared of their algebra, they'll prefer the y's, and that's fine. Okay, I'm going to do a second example for which the inverse is not a function, so that I can then talk about how you can tell whether the inverse is a function. So I'm going to go with g of x equals x minus 2 squared plus 1. The first thing then I'm going to do is rewrite it with y. Then I'm going to switch my x and my y. And then I have to solve for y. This one's going to take a few more steps. I got to subtract the 1 squared. Then I got to take the square root. When I take the square root of both sides, I get a plus or minus. And then I add the 2. I guess this is like the end of completing the square. So it's not like you've never seen anything like it before. But right away I can tell this isn't a function, because for any x I stick in, there's mostly going to be 2 different answers, which clues you in there it's not a function. Quadratics, parabolas tend not to have inverse functions. Now it's still an inverse. It's an inverse relation, but I'm not going to claim that it's a function, so I'm not going to write g inverse, because it's not a function. If you look at what happened here, let's see, that's 2, 1, and 0 would be 5. All right, so it's a parabola, something like this is g, and so its inverse, instead of having a vertex at 2, 1, has a vertex of 1, 2, and instead of going through 0, 5, goes through 5, 0. And so it goes this way. And if you remember back when we learned about functions, you can see right away this is not a function, because what we learned back in chapter 2 was the vertical line test, which said you can tell whether or not something is a function if you can see its graph by looking, and if you can draw a vertical line that crosses the graph twice, it's not a function. And that's exactly caused by this plus or minus here, because for any given x, there's one with plus and one with minus, and they're on top of each other. So that's the vertical line test. The new thing we're learning today is how to tell whether or not the inverse is going to be a function before you find the inverse. And if you think about the switching of x's and y's thing, these are 2 x's, well, the same x with 2 different y's, which means in the original function g, there were the same y that had 2 different x's. So we introduce now something called the horizontal line test. Now the horizontal line test does not tell you whether what you're looking at is a function. It tells you whether the inverse of what you're looking at will be a function. So if I go back up to my first example, f of x equals negative 1/2 x plus 1. Negative 1/2 x plus 1 is a y-intercept at 1/2 and a slope of negative 1/2. Well, I think I said 1, but it's y-intercept of 1 and a slope of negative 1/2. So that is f. Now, if I do the vertical line test, I can verify, because I can't cross this twice with a vertical line, that f is a function. To determine whether its inverse will be a function, I do the horizontal line test, and since there's not a horizontal line that crosses it twice, its inverse is also a function. Back in chapter 2, we introduced the term one-to-one. If you pass the vertical and horizontal line tests, we call that one-to-one. And a one-to-one function is a function and its inverse is a function. But like a parabola is not one-to-one, because although the parabola is itself a function, it passes the vertical line test, it fails the horizontal line test, which means its inverse will not be a function. So I have done what is an inverse. We found an inverse using ordered pairs. I talked about the graph of the inverse. We found 2 inverses from their equations. And I talked about determining if an inverse is a function. So the only thing left to do is verify that 2 functions are inverses. So allow me to give you a pair of functions, and then we will determine if they are inverses. F of x equals 3/4 x minus 6, and g of x equals 4/3 x plus 8. So these are two functions, and I do not know if they are inverses or not. I could graph them and look to see if they're reflections, but I'm not good at seeing lines and whether or not they're reflections. So I'm going to go back to the definition of inverse. The whole idea was if I stick a number into f, I'll get an answer, and if I stick that number into g, I should wind up back where I started. So if I do that with x instead of with a number, it tells me that if these are inverses, then g of f of x should be x. Now, if you're doing this formally, like not for this class, but formally, you're supposed to prove it both ways, although I have yet to ever see an example where one way worked and the other way didn't. So I'm going to do both anyway. So I'm going to do g of f of x. So I got to take g, and I got to replace the x with f of x, and then see how it simplifies. And if they are inverses, once I simplify this, what'll be left over is just x. So I have to distribute the 4/3. 4/3 times 3/4 is 1. That's promising. 4/3 times 6 is 2 times 4, which is 8. X minus 8 plus 8 is x. So yes, it looks like they're inverses. If I do it the other way around, I take f, 3/4, and I stick in g, 4/3 x plus 8 minus 6. Again, I'll distribute. That's 1x plus 2 times 3 is 6 minus 6, which is x. And that's how you verify two functions are inverses. You do composition, and what you have should simplify to x, and if it doesn't, they are not inverses. That concludes my notes. The homework is posted, so good luck, and let me know if you have questions.